Good morning, student. In your previous class, we have discussed about the kinetic gas equation, which is PV equal to 1 by 3 m n u RMS square. So, what do you mean by P? P is pressure. Here P is pressure, V is volume, M is what? M is mass of one molecule, n is number of molecules, and URMS is root mean square velocity. So if I take n, that is number of molecules, equal to Avogadro's number, that is capital Na, we can write PV equal to 1 by 3 m Na URMS velocity. Now this is your molar mass. This m Na equal to capital M. This is molar mass. Now we can write PV equal to 1 by 3 capital M U RMS velocity. Now if I write PV equal to 2 by 3 into 1 by 2 MURMS, we can write this PV, this expression in terms of kinetic energy. This is our kinetic energy. So we can write PV equal to 2 by 3 KE, that is kinetic energy. So we can write K kinetic energy will be 3 by 2 PV. This is for 1 mole. This is for 1 mole. Now for 1 mole we know that PV equal to RT. So we can write 1 mole equal to 3 by 2 RT. Here R is what? Gas constant, and this is the value of this is 38.314 joule per mole Kelvin. So this expression says that at this temperature, if T equal to 0, Kelvin, kinetic energy will be 0. So at this temperature, all molecular motion will energy for n moles. We can write n into 3 by 2 RT. So if I want to find out kinetic energy for one molecule, we can write 3 by 2 R divided by Avogadro's number to T. This will be equal to, this term will be equal to what? Boltzmann's constant, that is 3 by 2 kBT. So kinetic energy equal to half m u RMS velocity equal to 3 by 2 RT. Is not it? That is kinetic energy equal to half m capital M u RMS square equal to 3 by 2 RT. From this we can find out RMS value. That is the RMS velocity, that is u RMS square equal to 3 by 2 RT. So URMS equal to root over 3 by 2 RT by, sorry, there should be M, by capital M. So we can see from this expression that velocity is proportional to, RMS velocity is proportional to, directly proportional to temperature. So the faster the motion, so we can say that faster the motion of the molecules, kinetic, higher the kinetic energy, and if high the kinetic energy will be high, that means higher the temperature. Hence temperature is the measure of kinetic energy of all molecules. This is the kinetic interpretation of temperature. This is the kinetic interpretation of temperature. Now next is degrees of freedom. What do you mean by the degrees of freedom? It is the number of coordinates required to describe its motion or configuration. Or we can say that number of independent ways in which a particles of the system can absorb energy. Suppose this is a molecule and we want to specify the location of this molecule in space. So we need how many coordinates to specify it is our degree of freedom. For one molecule it has 3 degrees of freedom, is not it? Now if there are 2 atoms, now if this atom, this is allowed to move in y axis, z axis, this particle is also allowed to move in a y axis, z axis, but they are fixed in x axis. So there is some definite relation between them. So it cannot move in freely in x direction. So for the degrees of freedom will be 3. Its degrees of freedom is 3. So we can write 3 into 2 by there is some 1 relation between them. So minus 1. So this will be 5 degrees of freedom. So I will find degrees of freedom degrees of freedom. Degrees of freedom can be determined by relation, that is if f is the number of degrees of freedom, it can be find out 3 equal to 3n minus k. n is number of particles in the system and k is number of independent relations between the particles. Now for monoatomic gas, suppose the monoatomic gases are helium, neon, argon. So here n equal to, that is number of particles in the system is 1, the relation between them is 0. So f equal to number of degrees of freedom will be 3 into 1 minus 0, that will be 3. For diatomic gas, diatomic gases are nitrogen, oxygen, hydrogen, CO. So here n will be what? 2 and k will be 1. So our degrees of freedom will be 3 into 2 minus 1, that will be 5. In case of triatomic in case of triatomic gas, there will be two ways, one for the linear and other for the non-linear, one for the linear and other for the non-linear. So linear molecule are, suppose CO2, example CO2. In CO2 linear molecule will be such a way, so the relation between them is 2, so the degrees of freedom will be 3 into thrice n minus k, it will be 3n, that is 3 minus n will be, k will be 2, so the degrees of freedom will be 7. For non-linear, the examples are H2O, so it will be such way, so the number of independent relation will be 3, so in this case the degrees of freedom n will be 3, k will be 3, f equal to 3 into 3 minus 3, it will be 6. Next is law of equipartition of energy. So it states that, suppose we know for a molecule it has 3 degrees of freedom, and the energy kinetic energy of a gas molecule will be, kinetic energy of a gas molecule will be 3 by 2 kBT. So the law of equipartition of energy says that this energy will be equally distributed among its various degrees of freedom, and the energy associated with each degrees of freedom per molecule is half kBT. It will be half kBT. So this is the law of equipartition of. So the next is the specific heats of monoatomic gas. Now here for one molecule the degrees of freedom is 3, so we can write energy of, we know that energy of each degrees of freedom is half kBT. Now total energy of molecule will be 3 by 2 kBT. We can find out the total energy of 1 mole. How to find out? If I multiply by Avogadro's number, we can find out the total energy of one molecule, that will be 3 by 2 kb Na. So kb Na equal to R. So we can write 3 by 2 RT. Now the total internal energy of 1 mole of atomic gas, that is U equal to 3 by 2 RT. So we can find out the molar specific heat at constant volume, that is Cb equal to U by T. That will be 3 by 2 RT by R. This will be 3 by 2 R. Now what will be Cp? Cp will be, we know Cp minus Cv equal to R, that will be Cb plus R will be 3 by 2 R plus R, which will be 5 by 2 R. Now from this we can find out the specific heat ratio, that is gamma Gamma will be Cp by Cb, that is 5 by 2 R divided by 3 by 2 R, which will be 5 by 3 equal to I think 1.67. So this is the specific heat of monoatomic gas. Likewise, we can find out for diatomic gas and triatomic gas.